Now let's continue from our previous discussion on Compton effect. Uh, let's try to have an equation that gives us the kinetic energy of the scattered or the recoil electron. Now to start with, if I assume that nu is the frequency of the incident photon, and nu dash is the frequency of the photon after it collides with the electron, which is actually supposed to be at rest. So we have a photon and we have an electron. So in this case, now if I assume that m is the mass of the electron, so m is mass of electron, and 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 m naught is the rest mass of electron. So, so to convert it into a kind of statement, is that then I can say that the kinetic energy of the scattered electron that will be scattered, that will be the difference of the two masses times c square, and this must be equal to the decrease in the energy of the incident photon. So what is that decrease in the energy of the incident photon is h nu minus h nu dash. So I can say that from the above condition, I can say that the kinetic energy, say Ek, that is h times nu minus nu dash. Now, if I move on from here, I can think of writing h nu outside 1 minus nu dash by nu. This is Ek, right? And I can proceed from here and would like to convert this equation in terms of wavelength. So what am I going to get here is that this kinetic energy will be h nu times 1 minus lambda dash will come up and lambda will go down, because we know that nu is c by lambda. So this Ek must be equal to h nu times. So if I have here lambda, then this will be lambda minus lambda dash, right? So I can think of Ek equal to h nu times delta lambda. So this is delta lambda, and for lambda I can have here I have delta lambda in the numerator, and I can have lambda plus delta lambda in the denominator. So here, if we proceed from here, and we have the Compton scattering equation, say call this as equation 1, and if I go with the equation that we have for Compton scattering, that is delta lambda is it is h by m naught c times 1 minus cos, this is cos phi. So that's the case. Now I can use this thing in my original equation here for delta lambda. If I do that, what am I going to write is Ek. This Ek must be equal to h nu times for delta lambda I have h by m naught c times times 1 minus cos phi. Okay, this thing will come in the numerator, and in the denominator what I'll have is lambda plus h by m naught c times 1 minus cos phi. Okay, so that's correct. Okay, so from here we can move on. If we rightly remember, this is h nu, and this is h by m naught c, and basically what we have done is we have converted the frequency in terms of lambda. Now if I divide here this numerator by lambda, I will have to do the same thing here, and I'll have to do the same thing here. So what I'll have is, in the previous video, we have taken this alpha as h by m naught c lambda. You can check it in the previous video. So this ek is going to be h nu times alpha times 1 minus cos phi. This is going to come in the numerator and in the denominator. So here we have 1 plus alpha times 1 minus cos phi. And we better understand why alpha is here, because alpha is h by m naught c lambda. Now, from this equation, let us evaluate some physics out of it. Now, we can understand from this equation that this energy, this kinetic energy of electron, it can range. It can range from phi equal to 0 to phi equal to pi by 2. And we can have, if we take it 0, in that case ek will come out to be, from the above equation, it will come out to be 0, and for phi is equal to 0, and for phi equal to pi by 2, this e will come out to be h nu alpha divided by 1 plus alpha. Right. So what's going to happen here is that the electron can have all possible energies from 0 to h nu alpha by 1 plus alpha. Right. So from this, what can we conclude from here is, if we will go for further modification of this equation, what is going to be concealing here, what kind of discussions we can have, how we can interpret this equation, is in terms of the maximum energy of the recoil electron, is if we take into account the results that we have obtained. Now, what it states, if we take alpha equal to pi. Now, if we take alpha equal to pi in this equation, so for alpha equal to pi, we can have ek that we calculated as h nu twice alpha divided by 1 plus twice alpha. Okay, so pi means flatten kind of thing. Okay, now the point of discussion here is that from this equation, it's clear that the energy of the scattered electron, it ranges from what I said, it ranges from 0 to h nu 2 alpha by 1 plus 2 alpha. For the values of scattering angle theta that we have, theta of a photon, that ranges from 0 to pi. Right. So what do we conclude from here? Thus we can say that the maximum energy that the recoil electron can have is equal to this much. It is h nu times 2 alpha divided by 1 plus 2 alpha. Now, how can we translate it into something significant? Is that what it means is that it's not possible for a photon to transfer the entire energy to the recoil electron. And the maximum energy the photon can transfer to the electron is h nu 2 alpha by 1 plus 2 alpha. And this value is certainly less than h nu. So we can certainly say that this h nu times 2 alpha divided by 1 plus 2 alpha, it has to be less than h nu, because this alpha is not negative, it's positive, right? This alpha is positive. Now, if this alpha is positive, that means it's not possible for a photon to transfer the entire energy to the recoil electron, and we can understand from this equation that it's not possible for the photon to transfer all of its energy to the electron by virtue of getting this equation for kinetic energy equal to this, and this value is less than this because alpha is positive. So, students, let's solve a problem based on Compton effect. And we have already derived the equation for the Compton shift. And you can see the problem says that we have a photon of frequency nu, and this photon gets scattered through an angle phi from an electron assumed to be at rest. Now, the first thing it's asking us is for the expression of energy for the scattered photon. And then the next thing that the problem asks us is that we have a photon whose incident energy is 0.9 mega electron volts. And this photon is scattered through an angle of 120 degree. So what we have to do is to calculate the energy of the scattered photon. Now, to do this, to solve this problem, we would like to start from the Compton shift. So, to solve this problem, would like to start from Compton shift. So the solution, in solution, what we have basically delta lambda is h by m naught c 1 minus cos phi. Now this means lambda dash minus lambda is h by m naught c 1 minus cos phi. Now if I reverse it in terms of frequency, so this will be c by nu dash minus c by nu equals h by m naught c 1 minus cos phi. So we can see here this c will be multiplied, so here we'll have nu dash, so here we will have nu minus nu dash, so here is h by m naught c square 1 minus cos phi. Now we can take this there, this is nu minus nu dash is h nu dash by m naught c square times 1 minus cos phi. Now we can think of multiplying both sides by h nu, so we can have h nu minus h nu dash is h nu times h nu dash by m naught c square times 1 minus cos phi. So moving on in the same direction is what we have now. We have this equation that in order to make it simplistic in form, let me choose h nu as e and h nu dash as e dash. So this is e dash by m naught c square times 1 minus cos phi. Okay, so what am I doing here is for E I have h nu, and for E dash I have h nu dash. Okay. Okay, that's fine. So I can have this I can have this E now. So this E will be, this E dash will go on the other side of the equation. So plus E dash by m naught c squared times 1 minus cos phi. So here I will have E dash out. So this is 1 plus E by m naught c squared times 1 minus cos phi. All right, so this is E. But I want E dash, so E dash is E by 1 plus E by m naught c squared times 1 minus cos phi. That should be the case. Okay, so this E is h nu, that's understood. So I can come back. I can come back to the original form. So this is my E dash. Now this E dash will be h nu by 1 plus h nu by m naught c squared times 1 minus cos phi. All right, that should be the case, and then we will have, as we know, that we can substitute for alpha. Now, what's alpha is h nu by m naught c squared. So here E dash will be h nu by 1 plus, this is alpha times 1 minus cos phi. So E dash is going to be h nu by 1 plus twice alpha sine square phi by 2. So this will be the expression for the energy of the scattered photon. Now going back to the problem, we have to do some calculations. Like now what we have is, we have the energy of the incident photon is how much? It is 0.9 mega electron volts, and the scattering angle is 120 degrees. So calculate the energy of the scattered photon. So from here, when we'll move for the solution of this problem. Okay, so this is for, so what should I do now is what's given is the E is given as 0.9 mega electron volts. And what else I want? I want alpha. What is alpha in my case? It is h nu by m naught c square. H nu by m naught c square. So this alpha is 0.9 mega electron volt divided by this m. The rest mass energy is, it nearly comes out to be 0.5 mega electron volts. So this is 0.5 mega electron volts. So alpha is this 0.9 by 0.5, right? Now we have the formula for the energy calculation of the scattered photon as this E dash is equal to h nu by 1 plus 2 alpha sine square phi by 2. But at the same time, we have to evaluate sine phi by 2. So in our case, so we have phi given as 120 degree. So sine phi will go as sine of pi minus 120, and this is simply sine of 60 degree, and sine of 60 degree means sine of phi by 2, so that is sine of 30. So sine of 30 is equal to 1 by 2. So sine square of 30 will be 1 by 4. So we got to use the value for alpha and sine square phi by 2 and 0.9 mega electron volts, and that will give us the energy of the scattered photon. So what could be the possible solution here? So this is 5. So my E dash will be it will be 0.9 by yeah, it is 1 plus 0.9 by 0.5 into 1 by 4. So mega electron volts. So that should be the case, right? And when we'll calculate this value nearly comes out to be 0.47 mega electron volt. So this will be the energy of the scattered photon. Now let's see another problem. What we have, actually we have to prove that the energy of the scattered photon is less than this twice m naught c squared for a free electron if the scattering angle is greater than pi by 3. Now we already have the equation for calculation of energy of the scattered photon is it is h nu by 1 plus twice alpha sine square phi by 2. This is going to give us the energy of this scattered photon, which has already been deduced in the previous problem. Now here in this case, what's the condition is that this if I take this phi equal to pi by 3, what does that mean? That means that sine of phi by 2 will be sine of instead of phi I have pi by 3, so it will be pi by 6, and this sine of pi by 6 is simply 1 by 2, right? So I have sine square phi by 2. For that, certainly I will have the value equal to 1 by 4. Now what is the condition here? I mean, for this phi greater than pi by 3, if this phi is greater than pi by 3, what does that mean? That means this sine square phi by 2 will be greater than 1 by 4, right? Now this sine, from this condition point of view, this sine function, it's going to increase. It's an increasing function of phi. So for any value, what can we generalize here is that this phi being greater than pi by 3 means this sine square phi by 2 is greater than 1 by 4, and we can introduce a constant, say like this k times that this sine square phi by 2 is equal to k times 1 by 4. But what's the condition for k? This k has to be always greater or equal to 1. Only then the above condition can be satisfied. So if I use this condition for sine square phi by 2 in this equation and see what happens. Now what will I have if I use this case here? I will have E dash equal to h nu by this is 1 plus so what's here? This is 2 alpha. This is 2 alpha. We know that is h nu by m naught c square, right? Then here I will use dot 1 by 4k, okay, for sine square phi by 2. Okay, now this k, what's the important condition for k is greater or equal to 1. Now if this is the case, we would like to move on from here we will have what we will have in terms of energy here. So here we have E dash, and so here we have H nu. Now, if I write down this H nu as like this is 1 plus, it should be m naught c square plus twice H nu divided by m naught c square. Yeah, this should be like this. And I think I should have crossed this. This is two ones are, this is two twos are here. So 2 will come here, and we will have 2 here. So here I will have 2, and here I will have H nu, right? So this m naught c square can go up. So this is H nu times twice m naught c square, okay, divide by twice m naught c square plus H nu. It looks something like this. And where is K? Hey, come on, K. So K is here. So K will be here. So K will be here. So 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 here I will have K. Okay, so what should I do from here is I would like to divide numerator and denominator by H nu. So what will I get? I will get twice m naught c square by twice m naught c square by H nu plus K is equal to E dash. Now, this equation is a clear indication for what was proposed in our problem was that we have to show that the energy of the scattered photon is less than twice m naught c square. And we can see from this equation that this E dash is always less than twice m naught c square, because this K is always positive, and K is positive, and twice m naught c square by H nu, this is also positive, right? So this is also positive. And what does it mean? It means the maximum value for E dash for the scattered photon is twice m naught c square, right? So this quantity in the denominator, twice m naught c square by E plus K, is always greater than 1. And if this is always greater than 1, that means this E dash is always less than 1. How so large the value of energy of the incident photon will be?